All right, so welcome back. So let's carry on and hopefully try to build up a formula for surface integrals of vector fields. So remember those tangent vectors that we got to our surface S. They called them r sub u and r sub v. They represented sort of what direction you'd be moving on S when you move just in the direction of u in the region D of the UV plane, and how you'd move on S when you move just in the direction of V in the UV plane. Okay. And so since both of those vectors are tangent to the surface S at every respective point that they live on S, then their cross products will be perpendicular, right? Because we know that if we have two vectors that are both tangent, and we have their cross product will be perpendicular to both of them, so it should also be perpendicular to the surface itself. Okay? So for that reason, we call those cross products, RU cross RV, the normal vectors to the surface S. Analogous to how we call normal vectors to a plane, right? A plane is really just an example of a surface in space. And so to generalize the idea of normal vector to a plane, we have these kind of floating, changing normal vectors to a surface S. And to give them some kind of uniformity, the authors of the textbook and just in general like to make them all unit length. So we'll take the vectors RU cross RV and divide them by their lengths. This is what we call the unit normal vectors to S. And so as we range over all the points in the surface S, we have these different normal vectors N kind of sticking out. So I like to call it the sort of unit normal vector field on S. It's just a vector field on this particular surface, but it has everything to do with just this surface. So it doesn't make sense to talk about it outside of there anyway. Okay, and so as a kind of like big warning here, especially for this particular video, there was a choice made here to put r sub u first. I don't know why. I mean, perhaps you could think that choice was just alphabetical, and you might not be wrong. But if you switch that order, it will change the direction of these normal vectors n, right? Remember that rule of when you switch the order of a cross product, you negate the cross product itself, which is to say you change its direction. And so we might have need at some point to do that. We might actually be asked to do that at some point later. And so we're actually going to really need to mind what direction this cross product is actually pointing in, because it could be something that we're needing to call upon as we move forward to do surface integrals of vector fields. So just keep that in the back of your mind. And for that reason, it's always very good to have a picture of the surface S that you're talking about, and to have some kind of way to visualize then these vectors RU and RV that live on that surface. So in particular, we have for some surfaces a notion of what's called outward pointing normal vectors. Now, not all surfaces are going to have this notion be in a well-defined way. The ones that are what's called closed surfaces. So this is analogous very much to a closed curve in, say, the plane. A closed surface in space is one such that there is a three-dimensional solid whose boundary surface is that surface S. In particular, then, since there's a three-dimensional solid that's bounded by that region S, that'll be like the inside part of S. And so S will be something that breaks space into a sort of inside and outside, okay? Just like a sort of closed curve, or what do we call a loop or something in the plane, separates that into a sort of inside and outside. So my favorite examples of closed surface in space would be the sphere, probably my number one favorite. And then a pretty close second is what's called a torus, something that looks kind of like the surface of, let's say, maybe a bagel or a donut or something like this. You can see that both of these have a very clear inside and outside right? This has a very clear inside and outside. Notice too that they kind of don't have an edge on them. There is really no edge to these surfaces. And like the cone that we saw in the last video had an edge that was like the circle at the top. Well, these don't really have that quality. And so another way to say closed surface is to say that the surface S has no boundary itself or no edge to it, right? Okay, so for surfaces like this, then, we can really talk about outside and inside in a sort of well-defined way. And so the choice of one of those vector fields, either r sub u cross r sub v, or the other way around, r sub v cross r sub u, one of those choices will have that those vectors n will point outward. And so we'll call those the outward pointing normal vectors. Okay? I think the convention is that when we can have these, when we have a closed surface, they do want us to sort of always consider outward pointing normal vectors. But there is no really inherent need for that choice. We could be asked at any given time to consider inward pointing normal vectors. We would just like to now be able to distinguish between what those two notions are. So let's maybe take a look at it a little bit more closely. And I'll say that all of this is going to depend on the function r, which gives us these vectors r sub u and r sub v. So having that particular parameterization is, absolutely essential to all of this. So if we're given that parameterization, or if we've been able to come up with it by our own sort of wits, then how can we tell which choice for n will give us these outward pointing normal vectors? Well, we're going to like to have a picture of the surface at hand, and we're going to like to be able to draw some of these vectors, r sub u and r sub v, on that surface. And then from there, we'll use the good old right-hand rule. So let's suppose here we have the sphere, and I don't know what well, I guess we've given an example of, r of uv for the sphere, but let's just say this is just some generic pick. I don't know what it is. Then let's say that this is the vector r sub u, and this is the vector r sub v. I don't know what r was in this context. We'll just pretend like that's already known for us. Then if we have these two vectors here, in order to determine which one points outward, let's use the right-hand rule. So does r sub u cross r sub v point outwards? Well, let's see. If I took, this is going to be hard for me to do on the video, so you can just kind of follow along. If I took my right hand so that my fingers were pointing in the direction of r sub u, but curling in the direction of r sub v, it looks to me like my thumb would be pointing inward to the sphere. Uh-oh. So let's flip it around. Let's take my right hand and point my fingers in the direction of r sub v so that they curl towards the direction of r sub u. Now it looks like my thumb is pointing outward from the sphere. So it actually would be, in this case, the backwards cross product r sub v cross r sub u that gives us the outward pointing normal vector field. Now, one saving grace is that you really only need to determine which one's outward pointing at just like one good point on the surface, and that behavior will remain. The sort of parameterizations that we're going to consider in this class won't have this like sort of changing over. Like it'll be, unless there are two distinct pieces to the surface, which we're going to see in the next video. So if you have two distinct pieces to your surface that have then two different parameterizations, you will need to mind for each different piece. But for some nice thing like this that's just given to us in one piece, we can just test at one point. So we'll pick some point and evaluate the vectors r sub u and r sub v, and maybe even draw those down on the surface if you like, and then use either the right-hand rule or take the cross product yourself and draw that one down on there and see which one points outwards. And so the one caveat to this, though, is that you will need to pick a u and v where both the vectors r sub u and r sub v are not 0. There are going to be maybe some cases of some parameterizations that have small degenerate points in the uv plane. And basically, if you get one of those, then just pick a different point instead, and you'll probably pick a good one on your second pick. So maybe let's see this in action. So yeah, here again is that cross product that points outward. As you can see, it's the backwards one. So now that we've got all of that information, let's get the formula for the surface integral of not a function, but a vector field. So let's suppose that we have a vector field on space here that's given to us by P of xyz in the first component, Q of xyz in the second component, and big R of xyz in the third component. And we'll restrict that vector field to just the surface S, okay, which has been parametrized by the function R of uv. Okay, then we have now these vectors from this vector field F. I don't know how they're defined. That they don't have to have anything to do with the surface S other than that it's in their domain. So we'll see that then we have some vectors from F that live on S. And then we also have this totally other vector field on S that's given to us by the unit normal vectors, the outward pointing normals if it's a closed surface, or maybe some other direction that's specified to us if the surface is not closed. So then from those two vector fields, we can get a scalar valued function by just taking at each point along the surface the dot product of the vector from the vector field along that surface and the vector from the unit normal vector field. So I'll go see the vector field that's handed to us is F, and the vector field that's sort of inherent to the surface is N. Just take the dot product of those two at each point. That then gives us a number at each point of the surface. So that is to say a scalar valued function defined over the surface. And we know already how to take surface integrals of scalar valued functions defined over the surface. And so we'll do exactly that to this scalar valued function. So then the surface integral of the vector field big F along S is the surface integral of the scalar valued function that's given by f of r of uv dot product with n, the unit normal vectors. So you can write that like this, where this left side notation is new notation for the surface integral of a vector field, big F, and this right side notation is the still sort of abstract notation for the surface integral of this function, big F dot n. And that n should be bold. Oops, sorry about that. Anyway, so let's suppose that the choice of RU cross RV is what gives us the sort of outward pointing direction or whatever one is specified for us. So let's say then that the vector field n is given by that cross product divided by its length to make it unit everywhere. So then we know how to do this surface integral of a function. We can write it more explicitly then by pulling back to the region D of the UV plane that parameterizes our surface and integrating over that region the function that is given by f of r of uv dot the vectors n, but then we have to multiply by that sort of area work factor that the function r performed. And oh my gosh, lucky us, that length of that cross product is now in the numerator and denominator of this expression, and so it cancels out, which is rather nice. So that we get this much simpler looking expression for the integral of a vector field over a surface in space. It is just the double integral over the region D of the dot product of the vectors big F along the surface R of UV, dot producted with the cross product of RU cross RV, or possibly RV cross RU if that's the one that points outward, or if that's the one that you're explicitly told to be using in some other context. Okay, and so another phrase for this surface integral of F over S is what's called the flux of F across S. And if you are a student of, say, like physics or maybe EE, then this may be no news to you. If you are not, then maybe let's say a little bit more about what that is supposed to mean. So suppose that these vectors F are measuring, let's say, the velocity of some fluid that's flowing around in space at some particular moment of time, right? You know, a snapshot of time, and said, okay, at that snapshot of time, all of these vectors represent velocity vectors of this fluid at every point of space. Okay? Then the dot product, f dot n, that, remember, that describes the extent to which the two vectors in question point in the same direction. So it says, okay, so to what extent is this fluid that's flowing around moving in the same direction as this unit outward normal direction to the surface? So when S is a closed surface, this surface integral really measures the rate at which the fluid is moving out of S at that particular moment. And if it's not a closed surface, we can still think of it, this surface integral, as measuring the rate at which that fluid is flowing maybe through it in a particular specified direction, which they call n. Okay? So I think that's all for this video. Join us in the next one where we will do one long-winded example of this that really has two examples built into it. So we will see you then.